In this video, we are going to begin talking about quadratic equations, and we are going to start by graphing quadratic equations that are in vertex form. What this will mean is that in this video, you will learn how to apply knowledge of a parent function for a quadratic function, and we're going to use that knowledge so that we can graph functions that are quadratics as transformations of the parent. We are also going to be looking today at the quadratic equation exclusively in vertex form. So let's get started. First, just a little bit of information. You'll see in this table that there's a formula here, a general equation. This is the equation for all quadratic formulas. Notice that it has a few things that are familiar. There is an a value being multiplied out front. Inside of the parentheses that are being squared, there is an h value. And on the outside being added, there is a k value as well. These are all elements that we've already studied in the absolute value unit. So a couple of commonalities with them. First, h and k are going to be the vertex just like they were in the absolute value unit. A couple of other pieces is that the axis of symmetry is going to occur wherever the h value is. And what that means is that the parabola shape for a quadratic is going to fold in half or be symmetrical just like the V shape was. And last, we have a value out front that's going to tell us which way the parabola opens, up or down, depending on whether it's a positive number, meaning it opens up, or a negative number, meaning it opens down. I do want to point out that in this unit, the a value is not the slope of the right-hand side like it was in the absolute value functions. And we'll talk about that in a few minutes a little bit more. So with that information in mind, we have these nice pictures here of a blue parent function that's been translated in this red direction, h and k. So the shape of these parabolas, no matter where they move, up, down, left, right, or flipping over, the shape is going to be one that is U-shaped in nature. So let's look at graphing the parent function first. The parent function is going to be y is equal to x squared. Notice that the a value being multiplied out front is just 1, and there are no numbers inside with that x in the square, so that's like a plus 0, and there's no k value being added on to the end. Because of the way that this parent function is set up, our vertex is going to be hk, which is 0, 0. So in order to graph these, let's take 0, 0 and put it in the middle of our table. Now, because this is the first time we've looked at this, I'm also going to pull my calculator over here so that we can look at the table and see what's happening. So in my y equals, I'm going to put in x squared, and then instead of just clicking graph, I'm actually going to go to second graph so I can look at the table and get some values. You can see on my paper here, or in my calculator here, it started at 0, 0. If I pick some x values that are larger, like 1, 2, and 3, let's go back. There we go. Like 1, 2, and 3. You can see on the calculator at 1, the y value is going to be 1. The next ordered pair is 2, 4, and the next is 3, 9. If I scroll up some on my calculator, where'd it go? Let's see. Let me end the show for a second. There it is. Okay, so if I look on the negative side of my x's, so I'm going to scroll up a little bit. What do you notice about the values here? What do you notice at -1, -2, and -3? Do you see that the y values are 1, 4, and 9, which means that they are the same as what we just wrote down a moment ago? That's happening because parabolas and quadratics are symmetric around the vertex. So if I plot my vertex 0, 0, and then I look at the right hand side of it, I have to plot 1, 1, 2, 4, and 3, 9. Now, when I draw this line here in a moment, notice that this is not a straight line like the absolute values were. It has this curve that's happening here. So it's going to look more like that than a straight line. Now, let's go ahead and do our left side too, because we're not done yet. At -1, the function's up at +1. At -2, it's up at 4. And at -3, it's up at 9 again. So that means that our full parent function's graph looks like that. Notice that it is curved in shape. It's not a straight line, and that it opens up because the a value out here in the front is 1. So there's one other thing that I want you to notice about this when we're graphing these. Do you see how when you go from the vertex over 1 unit, 1 squared is 1, and so that's why this is up 1. And then from the vertex, if I go over 2 units, 2 squared is 4, so I rose 1, 2, 3, 4. And if I go over 3 units to the right, 3 squared is 9, so I went all the way up 9 units there. That pattern of 1, 1, 2, 4, 3, 9 is going to be very helpful as we begin to graph more of these if the a value is just a 1. So let's go ahead and slide our calculator over out of the way and try one of these where we're looking at vertex form and their transformations that have happened to it. So the first thing we need to do is find our vertex. So let's look at our equation here. You have 2 times x plus 3 quantity squared minus 8. The h is going to be the 3. Remember, we have to take that sign and make it a -3 when we pull the h out. And the k is -8, and that's going to stay as a -8. So I'm going to put those two values on my table here. And then I'm going to pick some x values that are close to -3. So I'm going to go smaller to -4, -5, and -6. And then I'm going to go larger to -2, -1, and 0. So with this vertex, I am graphing at -3 and then -8, which is going to be down here. Now we need to fill in the rest of this table so that we can do the rest of this graph. The a value in this baby function, if you will, because it's not the parent, it's a transformation of it, is 2, which means that we're going to have a vertical stretch. It's going to be stretched upwards or taller, more narrow than the parent function that we just graphed. So let's look at how that happens. Over at -2, if I plug in -2, so I evaluate the function at f of -2, that's going to be 2 times -2 plus 3 squared minus 8. So that is going to give me that -2 plus 3 is -1, -1 squared is +1, 2 times +1 is 2, and then when I do 2 minus 8, I get -6. So at -2, we're going to go down to -6. Now look at what just happened here. Remember how with the parent I said because the a value is just 1, I went over from the vertex 1 unit and then 1 squared is 1, so I went up 1. Look at what happened here. From the vertex I went over 1, 1 squared is 1, but this time because that stretch is doubling it, it's 2 times that squared value, I went up not just 1, but 1 times 2, which is 2 units from the vertex. Now let's go ahead and try to evaluate another one. Let's do f of -1. So I'm going to plug in that -1, 2 times -1 plus 3, quantity squared, minus 8. -1 plus 3 is 2, 2 squared is 4, 2 times 4 is 8, and then 8 minus 8 is 0. So at -1, we're going to be all the way up here at 0. Going from our vertex, we went over to the right 2 units, and then up 1, 2, 3, 4, 5, 6, 7, 8, because 2 squared is 4, and 4 times the a value, 2, is 8. All right, let's do one more of those. F of 0 is going to be 2 times 0 plus 3, quantity squared, minus 8, which means I have 0 plus 3 is 3, 3 squared is 9, 2 times 9 is 18, 18 minus 8 is equal to 10. So at 0, my value is going to be all the way up here at 10. Now, if I look at that again from my vertex, I went to the right 1, 2, 3 units. 3 squared is 9, but if I double it because of my a value, I'm going up 18. And if I count this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. See that rather than going over 3 and up 9, because 3 squared is 9, I went over 3 and up 18, because 3 squared is 9, and 9 times 2, my stretch, is 18. Okay, so now we've got half of it. The good news is you've done the hard work. Because of the symmetry that happens on the left-hand side, that means that at -4, it's also going to be -6 from down here. And at -1, it was 0, which means it's going to be 0 here. And at -6, it's also going to be 10. So we can graph that nice and quickly. And then once we have all of those points plotted, we can draw a nice U-shaped graph going through all 5 or 7 of those points. Okay, so a couple of things to notice with absolute value functions versus quadratic functions. The general form for an absolute value function was y is equal to a times the absolute value of x minus h plus k. For a quadratic function, we still have y is equal to a. This time it's times x minus h quantity squared plus k. You still have a, h, and k, but this time instead of absolute value bars, you have that square. And that square is what's causing this U shape to form. So let's do a quick summary of all of the different pieces of vertex form. If a is greater than 0, that means it's a positive number. What is happening with our graph? Is it opening up or down? It's opening up because a is positive, just like with absolute values. If a is less than 0, that means it's a negative number. Does the graph open up or down? Just like with our absolute value functions, it opens down. If the absolute value of a is bigger than 1, so that means it's a number that's like 2, 3, 4, so on, then it's going to have which kind of vertical dilation? A stretch or a shrink? That's a stretch. If a is a fraction, it's between 0 and 1, that means that it's going to have a shrink. And side note, that is a proper fraction, not just any fraction. And the parameter k is going to control the vertical shifting. Remember, that's the up-down movement. The parameter h is going to control the horizontal shifting, which remember is left and right. And finally, the vertex is going to be hk, just like before. I do want to point out and emphasize this note that a is not the slope of this function because it's that curved line this time. A is going to tell us how the shrinking or stretching is happening, and it's going to tell us which way it opens, up or down, but it is not going to tell us what the slope is. We cannot just draw straight lines in this unit for these curves. Okay, so let's do one more of these where we need to find the graph without actually using a calculator. So let's look at this problem. Y is equal to -2 times x squared. Now, if I write this in vertex form, I've got the -2, which is my a. What is the number that's inside of the square with the x for my h? It's 0 because there's nothing there. And what about the k value, this number that's added on out here? That's also 0 because there's nothing there. So that means that our vertex is at 0, 0. The direction, remember, that's depending on what a is because a is -2. That means it's opening down. Let's go ahead and get this table done so that we can graph now. So I'm going to put my vertex in the middle because that's always where it goes. And then I'm going to pick some numbers close by. So I'm going to look at 0, 1, and 2. And on the other side, I'm going to look at -1 and -2. So let's put 1 in and evaluate our function. F of 1 is -2 times 1 squared. 1 squared is 1. 1 times -2 is -2. Let's look at f of 2. That's -2 times 2 squared. 2 squared is 4. 4 times -2 is -8. So now because of symmetry, I can go around my vertex and say that this ordered pair is going to be -1, -2, and this ordered pair is going to be -2, -8. So now I've got my points. Let's graph. 0, 0 is going to be my center, my vertex. 1 goes down to -2. 2 goes all the way down to -8. -1 goes down to -2. And -2 goes all the way down to -8. So that gives me a graph that looks like this. Okay, notice that it does indeed open down because of that a value. You also may notice that if you want the quicker way to follow the pattern to graph, I went 1 to the right, and instead of going down 1 unit because 1 squared is 1, I had to double it because the a value is times 2. So 1 squared is 1, but 1 times 2 is 2, so I went down 2. When I went to the right 2 units, 2 squared is 4, but 4 times 2 is 8, so I went 8 units instead of just 4. All right, so let's talk about mins and maxes. This graph has a maximum value. It has a highest point. So for minimum, I'm going to write NA for not applicable. And for the maximum value, that maximum value on the y-axis is happening where y is 0. So that's my max. For the zeros, remember zeros are x-intercepts. So where do x-intercepts happen? They happen at 0, 0, the vertex, and no, we do not need a calculator to do that. Remember that if you do need a calculator because you don't have nice values, you can go into your calculator and look at the second trace and choose the second option for the zeros. You will have to put in left and right bounds for this one. It's going to ask you those questions down here at the bottom. Remember that you need to set the left bound on the left-hand side of the x-intercept, the right bound on the right-hand side of the x-intercept, and then for the guess, once it draws those 2 lines for the bounds, put it back on top of that 0 or that x-intercept and hit enter 1 last time, and it will tell you what that 0 is. Oh, I probably put that in too quickly. Let's try that one more time. Second trace. Oh, okay. Second trace. I'm going to choose zeros. My left bound is going to be over here. Hit enter a little more slowly. My right bound is going to be on the right-hand side of the x-intercept. So I'm going to hit enter. It's not thinking anymore, so that's good. I'm going to go back to where I think the 0 is and hit enter 1 last time. And it will tell me that it is at 0, 0. Okay, so, whoa. I'm going to have to look at why that's behaving funny. On your calculator, that should work without problem. I'll look at that and get back to you guys in class if you have questions about second trace. Okay, so let's get back to these notes. The Think and Write says, when you see an equation of a quadratic function in vertex form, how do you know if the vertex is a maximum or a minimum? So how can I know to answer these questions which one I'm going to have just by looking at the graph? Well, that depends on what A is, because remember, A tells you what direction it opens. If A is a positive number, so it's greater than 0, that means it's going to open which direction? If A is positive, it opens up, so that means it looks like that, and that means that it's going to have a minimum. If A is a negative number, if it's less than 0, that means that it's going to open down. And if it opens down, that means it's going to have this highest point, so that is a max. Okay, the last thing that we're going to look at today in these notes is working backwards. So in this problem, you are given a graph and you have to figure out what the equation is. The steps for doing this are first to find the general form of the parent graph. So we're going to write the formula up here where it says general form. Y is equal to A times X minus H, quantity squared, plus K. And now we're going to try and fill in these blanks. The vertex, HK, is easy to do because we can just look at our graph. That's 2, 1, 2, 3, -4 as our vertex. Now we are going to need to pick another point because if we plug in our H and K, notice that you have an X, a Y, and also that A value that we don't know yet. And that's not enough information because we have to find A. So we're going to do that by picking another point and graphing and substituting some information in. So I'm going to pick this one over here. That one is 0, -2. And I'm going to take those two values, the X and the Y, and I'm going to plug them in these two spots. So the Y value is -2, so I'm going to plug that in. I don't know A yet, but I know X is 0 at this other point. Once I have that, now I only have one variable, A, so I'm going to solve for it. To simplify that, I've got -2 is equal to A times -2 squared minus 4. -2 squared is 4, so that's -2 is equal to 4A minus 4. I need to add 4 to both sides, so that gives me 2 is equal to 4A, and then when I divide by 4 on both sides, I get A is equal to 1/2. So now I have A, and I know HK already, so I'm finally ready now to plug this in to my equation. So let's write our equation. Y is equal to, I'm using this general form up here, A, which is 1/2, times X minus whatever H is, so that's 2. That quantity is squared, and then I have plus K, which is -4 in this case. So that's my equation. Notice that this is a little bit more work than with the absolute value ones we were doing. You need to know your vertex, but then you need to pick another point and use it to substitute in and find what A is. And once you find A, then you can write your equation. Again, A is not just the slope, so I can't just count up 1, 2, over 1, 2, and call the slope 1. Notice that ordered pair that would make it a slope of 1 is not on the curve. Because it curves, there's no straight line for the slope. Okay, so with all of that, you should now be able to take your knowledge of the quadratic parent graph and apply it to functions using transformations so you can graph all sorts of functions that are in vertex form because you know the A value, you know H, and you know K. So go ahead and give the Now You Try problem a try.